All right, welcome everybody. Today we are going to talk about lesson number 34. This is an introduction to logarithmic functions. Please be advised that between section 3.2, 3.3, and 3.4, we're going to kind of be jumping around and mixing them all together. So don't be surprised if the homework is in a bunch of different sections. Just to set the scene about where a logarithmic function comes from, if you think back about exponentials, every single exponential that you were to graph, whether it's growth or decay, it will always pass the horizontal line test. Recall from chapter 1 that anything that passes the horizontal line test means that it has an inverse. So, of course, a logarithmic function is the inverse of an exponential. Starting off with the expression that's given right here, that is a logarithm. And the way you would say that is log base b of a, and then some qualifiers that a has to be greater than 0 and b has to be greater than 0. So to start, the best way to kind of remember about logarithms is to remember how they are in relation to exponentials. So if you take a look at these 8 logs in the boxes, you're going to start by rewriting them as exponentials. So there's lots of ways you might have learned how to do this. Some people may or may not have learned what's called the loop rule. The loop rule says you're going to start at the base, loop to the other side, and then come back. So if you were to do that, you could say that 3 to the third was equal to 27. Make that a little more 3-like. And that would, of course, be not only an exponential equation, but it would also be a true statement. Anytime you convert from a log to an exponential, what you're writing, of course, has to be true. So again, if you like the loop, feel free to write it. 5 to the first would be equal to 5. In the next one, if you want to get a little bit crazy, you could say that 125 is equal to 5 to the third. So feel free to play it fast and loose and write them on either side. For the fourth one here, 10 to the third would be equal to 1,000. 36 to the 1/2 would be equal to 6. Not only is this just really making sure you understand the relationship, but it's also just reminding you of a couple important exponential relationships. So 27 to the 2/3, that would be equal to 9. And then 5 to the 1/2 would, of course, be equal to the square root of 5. So not only do you have to be able to do what I just did, which is to go from log form to an exponential, you would also have to be able to work in reverse, which means if I were to give you the exponential, you would have to be able to write it as a log. So just to show you on the side here, how is it that you would go backwards? Well, suppose that I had given you 10 to the third equals 1,000. Again, perhaps just based on what you know about logarithms, you'd be able to rewrite that relatively simply, or just, there's actually another loop rule. Just like in the original problems where you start at the base, loop to the other side, and then come back, if you start at the base of the exponent, loop to the other side and come back, you would start by writing the word log. Start with the base, goes to the base of the log of 1,000 is equal to 3. For the one here, 5 to the 1/2 equals the square root of 5. Again, start at the 5, loop to the other side, write it as a log, same base of the square root of 5 is equal to 1/2. So you do have to be able to go back and forth from log to exponential and exponential to log with ease. So then the following 3 statements are true about the value of a logarithm based on the relationships between b and a. And just so you're aware, log base b of a, so b stands for the base and a stands for the argument. So that's why they use the letters b and a. So 3 things that are always true about the relationship between b and a. So if b is equal to a, then the value of the log must equal 1. And to show you an example of where that was true, if b is equal to a, that would be this example right here. Because b and a are equal, the log must be equal to 1. If b is less than a, then the value of the log must be greater than 1. So if b is less than a, then the value of the log must be greater than 1. And if you kind of look above here, let's find all the places where that's true. So all the values where b is less than a, that would be this one, this one, this one. All the places where b is less than a, notice that all of those solutions are clearly bigger than 1. Then finally, if b is greater than a, then we can say that the value of the log must be, you guessed it, less than 1. And if you go back above here, so if you look at all the circumstances where the b is greater than the a, that would be this one, this one, this one, and this one. And hopefully you would agree that in all those cases, the value of the log is clearly less than 1. Sometimes it's a fraction, sometimes it's negative, but regardless, it's always less than 1. So kind of keeping that in mind, look at the next 6 where they're asking you to evaluate. So if they're asking you to evaluate, they're basically asking you to find the value of the log. The best way to do this is to think about the following. Think about it as an exponential. If you're talking about a, b's, and x's, then what you're really asking yourself is b to the what is equal to a. So the base to what power is equal to the argument. So in number 1, f of x equals log base 4 of x if x is 16. So what you're being asked to find is log base 4 of 16. So again, if you think of this as an exponential, the question that you're answering here is 4 to the what power equals 16, and hopefully you can see that that's 2. In the next question, you would be asked log base 3 of 3. 3 to what exponent is 3? That's a 1. Log base 2 of 32. 2 to the what power is 32? That's 5. In number 4, log base 3 of 1. 3 to what power is 1? Has to be 0. Log base 4 of 2. So 4 to what power becomes a 2? Well, how does a 4 become a 2? You take a square root, and of course a square root is a 1/2 exponent. Notice that in number 6, you have an log with no base. As I'm going to remind you below, when you see an log with no base, you of course assume it to be 10. So this is really log base 10 of 1 over 100. 10 to what exponent gives you 1 over 100? Well, to become 100, you would square it. And to have it go to the bottom of the fraction, you of course would have to make it be negative. Again, just compare those 6 problems to the 3 rules that are written above, starting with the fact that if b and a are equal, so that's what's happening in number 2. Remember, if the base and the argument are equivalent, you have to get a 1. Then the scenario in the middle, all the cases where b is less than a, so that would be number 1. That would be number 3. In all those instances, notice that the answers that you get are, of course, greater than 1. Last but not least, think about all the places where the b is greater than a. So that would be in all of the remaining examples. And of course, all of those answers should be less than 1. So speaking of bases that don't, or logarithms that don't have an explicit base, that is base 10, and that is what we call the common logarithm. Those can mostly only be evaluated using a calculator unless they happen to be a power of 10. So if you have your calculator handy, take it out. If you turn it on, you should see the log button on the left-hand side near the bottom. And you're just going to go ahead and calculate the following log of each. And again, our normal rounding conventions from this point forward are going to be 3 decimal places. So if you calculate the log of 5, you should get 0.699. The log of 10 is, of course, an integer 2, 10 squared. And the log of 115 is 2.061. So there are some problems where you're going to have to use a calculator, and then sometimes you're not going to have access to it. And we'll try to talk about both of those scenarios. Then take a look at the next set here. So I give you a logarithmic expression in the left-hand column. I ask you in the middle to evaluate the logarithm. If it's an integer, tell me what it is. If it's not an integer, then tell me what 2 integers it's between. And then we're going to do a calculation over there at the end. So for each of these problems, log base 2 of 1/8, you might want to think of it as an exponential. So in number 1, the question that you're actually solving is 2 to the what is equal to 1/8. In the next one, the question you're actually solving is 2 to the what is 9, and 4 to the what is 21. So again, logarithms are nice, but you should always really think of them in terms of the equivalent exponential, especially if you're trying to solve them mentally. So 2 to the x equals 1/8. Well, I can write that as 2 to the x equals 2 to the negative third. Those are, of course, like bases, which means that my answer has to be x equals negative 3. Obviously, that's an integer. For the one in the middle, 2 to the x equals 9, well, that is not something that is going to be a nice integer value. So you're going to think about the integers that are nearby, which if you think of 2 to the third, that of course would be 8. Whereas if you think of 2 to the fourth, that would of course be 16. So what two integers is the answer going to be between? It's going to be between 3 and 4, obviously closer to 3 because 8 is closer to 9. Similar story for 4 to the x equals 21. So that's not going to be a nice number. So I'm going to remind myself 4 squared is 16, where 4 cubed is 64. So that means that my answer to this log is going to be between 2 and 3, probably closer to 2 because 16 is closer to 21. So for each of these values, you can also take what's given to you, log base b of a, and you can use the calculator to find the log of a divided by the log of b. Notice that there's one division bar, and notice that each of the values gets their own log. So log on top and log on the bottom. So again, if you have your calculator handy, you're going to do log of the argument, which is 1/8, divided by log of the base, which is log of 2. If you're using a graphing calculator, which I'm sure all of you are, just make sure you note that when you press the log button, it automatically opens a parentheses for you. So you have to make sure you close it between the numerator and the denominator. And if you go ahead and do that for the first one, you should get -3. For the one in the middle, you're going to go ahead and calculate the log of the argument, which is 9, divided by the log of the base, which is 2. Log 9 divided by log 2 is 3.170. And again, please round to 3 decimal places. Finally, you're going to go ahead and divide the log of 21 divided by the log of 4, and that is going to give you 2.196. You're going to want to go ahead and confirm. You said this should be between 3 and 4. Look at that. Between 2 and 3. Look at that. So it's a beautiful thing. It's so beautiful, in fact, that it has a name. It's actually called the change of base formula. And the change of base formula says the following. If you're ever asked to calculate log base b of a, you can do so by calculating log of the argument divided by the log of the base. Doesn't matter which value is bigger or smaller. It's always the log of the a argument divided by the log of the b base. And again, make sure it's a log on top and bottom, and watch your parentheses. If your calculator opens one for you, please make sure that you close it. So now go ahead and take a look at the next side, and we're going to go ahead and talk about our old friend E. You obviously should all know about E, but let's just do a refresher. So you are going to consider the expression 1 plus 1 over n to the n. Probably it's obvious, but just in case, please make sure that you know that that is equivalent to 1 plus 1 over x to the x. And I say that really only for graphing calculator purposes. You can see that I filled these in for you just to kind of save time, but I'm pretty certain that each of you could plug this into your calculator and evaluate it for each of these different n's. So n is obviously getting bigger and bigger and bigger. Think about what's happening as n is getting bigger and bigger and bigger. 1 divided by n. As you divide 1 by a larger and larger and larger number, you're actually getting a smaller number, but then you're going to be raising it to an increasingly higher power. So if you were to make all the n's equal to 1, you would get a value of 2. 10 would give you 2.594, and then obviously you can fill in the rest of those values as you see them. And then hopefully you would realize that once x gets larger and larger and larger, you can see that all the y values are kind of starting to converge around a certain value. That is, again, called a limit. Remember, if you're getting closer and closer and closer to a value, that's called a limit. So we would summarize that below as n goes to infinity, because again, even though we're technically stopping here at 10 million, you're getting infinitely large, which means you're going to infinity. Then the value of that expression is getting closer and closer to 2.718. And hopefully you can remember that that is, of course, E, and that is the natural base of a log. When it comes to calculus, pretty much it's all natural logs as opposed to being log of any other base. So that's where we're really going to focus our efforts. And then a little note about that. So a log whose base is E is called a natural logarithm. If you wanted to write that, instead of writing log base E of A, you would write it as the ln of A. So that stands for the natural log. And in case you're wondering, the reason why it's ln and not nl is because it started off as a Latin phrase and they do their words in reverse. The good news is that all properties of logarithms that exist for any base besides e also has to be true for natural logarithms. So notice again here, I have another change of base formula. So we're just going to extend upon what we had on the previous slide. So remember that log base b of a is equal to the log of a over the log of b. And because the rules have to be same for the natural log as well, it's also equal to the ln of the argument divided by the ln of the base. And again, we are actually going to see ln's way more than you probably ever have before. That's really just more of a calculus thing. So a lot of the times we're going to be using the ln button instead of the log. It's less to write anyway. Finally, I want to go ahead and solve some logarithmic equations. Note that these are logarithmic equations because they have equal signs and because they all have logs. You are going to try to leave your answer in exact form if possible, and otherwise you're going to go ahead and round it to 3 decimal places. So take a look here at the first one. Log base 9 of x is equal to negative 2/3. Again, whether you think of it as a loop or just as a relationship, you can think of it like this. So 9 to the negative 2/3 equals x. Again, don't just jump right to the decimal. A lot of times they say leave it as an exact answer, which means you have to try to write it using properties of exponents, so not turning it into a decimal. So think about 9 and then the negative 2/3. So negative 2/3, I'm going to apply just the negative, and I'm going to write this as 1/9 to the 2/3. You can then also write that as the cube root of 1/9 squared, which means you can actually write this as the cube root of 1/81st. And it turns out that that would actually be the answer that I'm looking for. So the cube root of 1/81. Again, there will be times where decimals are allowed, but you should try to get in the habit of giving exact values if at all possible. Here in the next one, starting with the 3, raising it to a negative 3, that's going to give you 2x plus 1. 3 to the negative 3, that's 1/27th. You're going to subtract the 1, and that's equal to 2x. You're then going to find a common denominator, so 27/27ths, which means that negative 26/27ths is equal to 2x. To get the x by itself, you're going to multiply both sides by a half or divide by 2. So if you do that, you're going to get equals negative 13 over 27. So again, try everything you can to get the answer to be exact. Most of the time, the only times you can't get an exact answer are something with e's. So notice this is the ln of 2x minus 1 to the 3rd. You would, of course, have to remember there's an e there. So turn it into an exponential. E cubed equals 2x minus 1. You would, of course, add the 1 and then divide the whole thing by 2. Turns out that most of the time that actually is a fine answer. If you actually wanted to calculate it, you'd of course have to do the entire numerator first and then divide the whole thing by 2, and you would get approximately 10.543. I think in the homework tonight, it says you can round to 3 decimal places, but again, it's good practice for later lessons to just try to keep it exact. Okay, couple more. So no number here. So 25 to the x is equal to 5 radical 5. I look at that problem and man, it's just screaming 5s. So I'm going to rewrite 25 as 5 squared. So that's 5 to the 2x. This is 5 to the 1st and then 5 to the 1/2. So because it's all now base 5, this is 5 to the 2x equals 5 to the add the exponents, 3/2. So 2x is equal to 3/2. Remember that dividing by 2 is the same as multiplying by 1/2, which is why you get a value of x equals 3/4. ln of x plus 3 equals 5. That's a base e to the 5th equals x plus 3, which means e to the 5th minus 3 is going to be your answer. I would actually be fine with that, but if you want to make it 145.413, who could blame you? Last but not least, you're going to go ahead and again, if you're thinking of it as the loop, this x plus 2 should stay together. So this is going to be 2 to the x plus 2 equals 9. Think back to the first lesson of exponentials. The only way to solve an exponential equation, if you do not have like bases, which you don't, is you're going to have to use the graphing calculator and the intersect feature. I'm relatively confident that you could do that. And if you do that, you're going to get 1.170. So I don't think that anything was really brand new, but certainly important to review. Let's go ahead and take a look at the homework. So the homework is in the book. I'm going to try to get us back in the book as much as we can to save everybody a little bit of paper. So homework 34, it's in 2 different sections. So in section 3.2, you're going to do 1 to 29 odd. And then in section 3.4, you're going to do 75 to 87 odd. I know it might look like a lot of problems, but I promise it is not. You should be able to do the entire thing, I would guess, in 15 minutes or less. So thanks very much for tuning in, guys, and we will catch you next time.